We will now continue with our study of electric potential by solving problems using the results we obtained in the last class. Now, to begin with, let's do a review. Tell me, what is the expression for electric potential at a point distance r from a charge q? Alright, the electric potential at a distance r from a charge q is V equal to kq over r. Now, if the charge is a positive charge, the potential will be positive, and if the charge is a negative charge, the potential will be negative. Now, another relation I would like you to know: what is the relation between electric field and electric potential? Can you recall that equation? What is the relation between electric field and electric potential? Well, the famous equation we talked about yesterday, dV by dr. E, electric field, is negative of the rate of change of potential. E equal to negative dV by dr. Right. And when you write this specifically for the x direction, we will say Ex equal to negative dV over dx. That means electric field can also be measured in the unit called volt per meter. Now, if you ignore the negative sign, I can write dV equal to E dx. Well, all these relations you must be familiar with in order to solve problems. Alright, let's start solving a problem. Example 1. An infinite plane of surface charge density sigma equal to positive 2.5 microcoulomb per meter squared is in the YZ plane. What is the magnitude of the electric field in Newton per coulomb and in volts per meter? What is the direction of the electric field for positive values of x? Well, actually, this is from a previous lesson that we had already done. It's a very simple problem. Is that right? Okay. What we have is an infinite plane charge that is in the YZ plane. By now you know this is the x-axis, the y-axis, and the z-axis. The plane is in the YZ plane, and the surface charge density is positive 2.5 microcoulomb per meter squared. Now, electric field due to an infinite plane of charge density sigma. Now, what is the expression for electric field near an infinite plane of charge density sigma? We did that in the 2 classes ago. Will be E equal to sigma over 2 epsilon naught. That means the electric field at any point near that charge will be sigma over 2 epsilon naught. We know sigma, that is 2.5 microcoulomb per meter squared. 2.5 times 10 to the negative 6. Epsilon naught is 8.85 10 to the negative 12. That gives the electric field 1.41 times 10 to the 5 Newton per coulomb. Well, what's the B part? Well, this is in Newton per coulomb. Can you express the same electric field in volt per meter? If you remember the little assignment I gave you, extra credit assignment last class, to show that Newton per coulomb and volt per meter are the same thing. So 1.41 times 10 to the 5 Newton per coulomb is the same as 1.41 times 10 to the 5 volt per meter. And what is the direction of this electric field? Well, for positive values of x, the electric field is directed in the positive x direction. Alright, let's look at another part of the problem. What is the potential difference VB minus VA when point B is at x equal to 20 centimeter from the charge or from the origin? We assume that the charge is at the origin, and point A is 50 centimeter from the origin. We need to find the potential difference between these 2 points. Well, you remember that equation. Delta V equal to negative E dr, or delta V equal to negative E delta R. Or specifically for the x-axis, we can write it as delta V equal to negative E dx. So this dr is the distance between the 2 points. Delta V corresponds to the potential difference between the points, and E is the electric field. So the potential difference between the 2 points is negative of E dr. VB minus VA. Delta V is potential difference between the points A and B. VB minus VA equal to negative E times x1 minus x2. dr is x1 minus x2. And this is our x1 and this is our x2. x1 equal to 0.2 meter. x2 equal to 0.5 meter. So we have a negative E, negative 1.41 times 10 to the 5. We just calculated the electric field, times x1 minus x2. That will be 4.23 times 10 to the 4. You notice that the 2 negatives, 0.2 minus 0.5 is negative. And that negative with this negative become positive. So tell me, which of these 2 points is at a higher potential? Alright, anybody tell me which of the 2 points A or B is at a higher potential? Well, if you remember, the direction of the electric field is the direction of decreasing potential. Therefore, B is at a higher potential than A. Alright, let me also ask you, what is the basic definition of potential difference between 2 points? Remember, a volt. What is the meaning of a volt? Volt is joules per coulomb, work done per unit charge. Now, the potential difference between points A and B is 4.23 times 10 to the 4 volt. Means in order to move 1 coulomb of charge from A to B, we need to do this many joules of work. So 4.23 times 10 to the 4 joules of work need to be done to move 1 coulomb of charge from A to B. Alright, that's the meaning there. So we found the potential difference VA minus VB. Alright, how about the next one? How much work is required by an outside agent to move a test charge Q0 equal to 1 nanocoulomb, 1.5 nanocoulomb from A to B? Well, if you understood what I said earlier, potential difference between A and B is 4.23 times 10 to the 4 volt. Means in order to move 1 coulomb of charge from A to B, the work that needs to be done is 4.23 times 10 to the 4 volt, 10 to the 4 joules. Therefore, if you want to move 1.5 nanocoulomb from A to B, what is the work that needs to be done? VA minus VB is a measure of the work done per unit charge. that is moved from A to B. Therefore, work done to move 1.5 nanocoulombs will be work done per unit charge multiplied by that charge. That will be W equal to 1.5 times 10 to the negative 9 coulomb, the amount of charge multiplied by the work done per unit charge, and that is 6.35 times 10 to the 4 joules. So here we clearly use the relation between electric field and potential difference. Okay, let's look at another problem. A positive charge of magnitude 2 microcoulomb is at the origin. What is the electric potential V at a point 4 meter from the origin relative to V equal to 0 at infinity? That is the guidelines that we have been following. The electric potential at an infinite distance from a charge is 0. How much work must be done by an outside agent to bring 3 microcoulomb of charge from infinity to R equal to 4 meter, assuming that the 2 microcoulomb charge is held fixed at the origin? As I have told you earlier, read the question carefully and see whether you understand it. Well, if you don't understand a question, you cannot do it. So, picture the problem. A positive charge of magnitude 2 microcoulomb is at the origin. Now here, this is the origin, and we have a 2 microcoulomb, positive 2 microcoulomb is at the origin. What is the electric potential V at a point 4 meter from the origin? This is the distance 4 meter from the origin. What is the electric field due to a charge at a distance R from the charge? I just wrote down in the beginning. The electric potential at a point distance R from a charge is KQ over R. So VR, potential at a distance R, equal to KQ divided by R. K is 9 times 10 to the 9. Q is 2 microcoulomb, 2 times 10 to the negative 6. And R is 4 meter. And that will be 4.5 times 10 to the 4 volt. Alright. Now tell me, we say the potential at this point is 4.5 times 10 to the 4 volt. What is the meaning of that? What is the basic definition of potential at a point? Well, potential at a point is a measure of the work done in bringing a unit charge from infinity to this point. If I want to bring a unit charge, how much is a unit charge? 1 coulomb. If I want to bring 1 coulomb of charge from infinity and keep it at this point, I need to do this much amount of work, 4.5 times 10 to the 4 joules of work. Remember, a volt means joules per coulomb. Alright, in that case, if I now have to bring 3 microcoulomb charge from infinity to this point, how much work do I need to do? You can do that now. So, work done to bring 1 coulomb of charge from infinity to x equal to 4 is this, 4.5 times 10 to the 4 joules. Therefore, work done to move 3 microcoulomb from infinity to x equal to 4 will be work done per unit charge multiplied by the amount of charge. So that will be the amount of charge, 3 microcoulomb, multiplied by work done per unit charge. That is 0.014 joules. Alright, is there another part from this problem? No? Okay, let's do another one. Part C, yes, there is another part. how much work must be done by an outside agent to bring the 2 microcoulomb charge from infinity to origin if the 3 microcoulomb charge is first placed at r equal to 4 meter and is then held fixed. Now that means you got to assume that this 2 microcoulomb is not there, but the 3 microcoulomb is there. That means that 3 microcoulomb will produce a potential at the origin. Now, what is the amount of work you need to do then to bring the 2 microcoulomb and keep it at the origin? That is what the question means. Okay, now we have a 2 microcoulomb at x equal to 4. No, we have a 3 microcoulomb at x equal to 4, not a 2 microcoulomb. So we need to correct that. We have a 3 microcoulomb is at x equal to 4. There we have a 3 microcoulomb here. So there is nothing at the origin. I've removed the charge from the origin. Alright? The potential at the origin due to the 3 microcoulomb. Now did you make that correction there? The amount of charge placed at x equal to 4 is not 2 microcoulomb, it is this 3 microcoulomb. So make that correction. That will be 3 microcoulomb. We have the 3 microcoulomb placed at x equal to 4. So, what is the potential at the origin due to this 3 microcoulomb? It will be V equal to KQ over R. Let me take off those things. So, V equal to KQ over R, where Q is now 3 microcoulomb, R is 4 meter. That will be K times Q, 3 microcoulomb divided by 4. That is 6,750 volt. The potential at the origin due to this 3 microcoulomb is 6,750 volt. What does that mean? Give me a sentence to explain what that means. It means 6,750 joules of work need to be done to bring a unit charge, 1 coulomb of charge, from infinity to the origin. Now what are we supposed to find? We need to find how much work needs to be done to bring this 2 microcoulomb from infinity to origin. Well, this 6,750 volt means joules per coulomb is the work that needs to be done to bring 1 coulomb of charge from infinity to origin. Therefore, work needed to bring 2 microcoulomb from infinity to origin will be the 2 microcoulomb multiplied by work done per unit charge. 2 times 10 to the negative 6 coulombs times 6,750 joules per coulomb, and that is 0.014 joules. What is it that you notice? It's the same amount of work. In other words, you first had a 2 microcoulomb placed at the origin, and we calculated the work done to bring a 3 microcoulomb from infinity to keep it here. That was 0.014 joules. In the second case, we kept that 3 microcoulomb here and calculated the work done to bring the 2 microcoulomb from infinity to the origin, which is the same quantity. Well, I hope you understand that concept. Another problem. 3 point charges are on the x-axis. Q1 at the origin, Q2 at x equal to 3 meter, and Q3 at x equal to 6 meter. Find the potential at the point x equal to 0, at x equal to 0, y equal to 3, if Q1 equal to Q2 equal to 2 microcoulomb, if Q1 equal to Q2 equal to 2 microcoulomb, and Q3 equal to negative 2 microcoulomb. Alright, again, picture the problem. Draw a diagram of the picture. What do we have? We have 3-point charges Q1 at the origin, Q2 at x equal to 3, Q3 at x equal to 6 meter, and find the potential at the point x equal to 0, y equal to 3. This is the point where we want to find the electric potential. Well, in the first case, Q1 equal to Q2 equal to Q3 equal to 2 microcoulomb. All of them are positive charges. That means the potential at point P due to each of these charges will be positive. Well, what is the equation for potential at a point due to a point charge? KQ over R. That means we need to figure out the distance between the charge and the point. Well, the distance between Q1 and P is 3 meters. What is the distance between Q2 and P? It is this. That will be square root of 3 squared plus 3 squared. Alright? And the distance between Q3 and P will be R3. What will that be? It will be square root of 3 squared plus 6 squared. Alright, let's do that. If R1, R2 and R3 are the distances of Q1, Q2 and Q3 respectively from the point 0, 3, we have R1 equal to 3 meter, R2 equal to square root of 18 meter. You see, 3 squared is 9 plus 3 squared. Square root of 9 plus 9 is square root of 18 meter. And R3 is square root of 6 squared is 36. 36 plus 3 squared is 45. So we now know the distances. We can find the potential at P. Well, in the first case, we have each of the charges is positive 2 microcoulomb. Potential at P due to Q1 is KQ1 over R1, and that will be 9 times 10 to the 9 times 2 times 10 to the negative 6 divided by 3. That is 6,000 volts. Alright, what is the potential at P due to Q2? Will be KQ2 over R2, and Q2 is the same as Q1. So that will be KQ2 over R2 is square root of 18. And that is 4,243 volts. And what is the potential at P due to Q3? Will be K equal to KQ3 over R3. That will be KQ3 is the same, divided by R3 is square root 45. That will be 2,683 volts. So what is the total potential at P due to all these 3 charges? They are all positive potentials, so we add them all up. The total potential is 12,926 volts. Alright, tell me, what does that mean? That the total potential at this point P is 12,926 volts. It means in order to bring a unit charge, that is 1 coulomb of charge, from infinity to point P, we need to do 12,926 joules of work. Potential is joules per coulomb. Alright, in the second case, we have Well, we didn't do that second part over here. Let's go back and do that. In the second part, Q1 equal to Q2 equal to 2 microcoulomb and Q3 equal to negative 2 microcoulomb. So, what is the total potential? The potential due to Q1 and Q2 will be positive. So, you will add V1 plus V2 and the potential due to Q3 will be negative. So, the result there will be 6,000 plus 4,243 minus 2,683 will be the potential at P due to these three charges. When the charge is negative, the potential it produces will be negative. Alright, let's now go and do the other one. Example 5. A sphere with a radius 60 centimeter has its center at the origin. Equal charges of 3 microcoulomb are placed at 60 degrees intervals along the equator of the sphere. What is the electric field at the origin? What is the electric not the electric field? What is the electric potential at the origin? What is the electric potential at the North Pole? Well, I'm looking for my basketball. You know how handy that comes when we deal with spheres. Now, here is the sphere. What are we supposed to do? And what do we have? We have equal charges of 3 microcoulomb are placed at 60 degrees intervals along the equator. Now, look at the equator of the sphere. This is the equator of the sphere. Now, if you place charges at 60 degrees interval, how many charges can be placed along the equator? Well, you can place 6 charges because the total degrees for the equator is 360. And at 60 degrees interval, you place a charge of 3 microcoulomb. So you got 3 microcoulomb, a 3 microcoulomb, a 3 microcoulomb, like that, 6 of them in equal intervals along the equator. We need to find the electric potential at the origin. The origin is the center of the sphere. We also need to find the electric potential at the North Pole at this point. Alright, well, once you have pictured, visualized the problem, let's draw a diagram. This is the equator of the sphere, and I have 6 charges, each of them 3 microcoulomb, placed at intervals of 60 degrees along the equator. First, I need to find the electric potential at the center. Well, the most important quantity you need to find the electric potential at a point is the distance of the charge from that point. Now, if you notice, each of these charges is at the same distance from the origin. And what is that distance? That distance is the radius of the sphere, which is given to be 60 centimeter. So we know the distances of all the charges. We know all the charges. So what all we need to do is find the potential at the center due to one charge, due to Q1, which will be KQ over R, R equal to 0.6, and then multiply that by 6. Is that right? Because each of them will contribute the same potential at the origin. So Q1 equal to Q2 equal to Q3 equal to Q4 equal to Q5 equal to Q6 equal to 3 microcoulomb. The distances of all 6 charges from the origin are all of them equal to 0.6 meter. The potential due to each of these at the origin therefore is the same, what is the total potential therefore? Each of them will contribute kq over r. Therefore, the total potential at the origin will be 6kq over r. And that will be 6 times k. Q is 3 microcoulomb. R is 0.6. And that is 2.7 times 10 to the 5 volt is the potential at the origin. Well, next we need to find the potential at the North Pole. And again, the first thing we need to figure out is what is the distance of a charge from the North Pole. Now, if you can visualize the distance of a charge from the North Pole, that distance is actually the hypotenuse of a right triangle. And what are the legs of that right triangle? This radius and this radius. You see, if you draw a line from the center to the North Pole, draw a line from the center to the North Pole, that will be a radius. Now that is what I have actually done here. This is a line from the center to the North Pole, that is the radius, that is 0.6. And the distance from the center to a charge is again the radius, that is 0.6. Now, the distance of the North Pole from a charge is the hypotenuse of that right triangle. Now, what is the length of the hypotenuse? That will be square root of 0.6 squared plus 0.6 squared. I hope you got the picture there. The distance of the North Pole from each of the charges is the same. And that will be this distance, that will be square root of 0.6 squared plus 0.6 squared, that is 0.85 meter. And therefore, all the 6 charges are the same, and all the 6 distances now are the same, and therefore the potential at the North Pole is 6 times kq divided by r, where r is 0.85. So the total potential is 6 times k times q is 3 microcoulomb divided by 0.85. That is 1.9 times 10 to the power 5 volt. All right. We will now look at potential inside and outside a spherical charged shell. Well, we are back with our shell. We talked about it in the last class. Tell me, we have a spherical shell, again my basketball. We have a charged spherical shell. What is the electric field inside the charged spherical shell? You remember the experiment done by Faraday? Yes, the electric field inside a charged shell is 0. Therefore, what is the potential inside the charged shell? Well, let's look at the relationship again. We have the relation between electric field E equal to dV by dr. Therefore, dV equal to E dr, or the potential V equal to integral of E dr. Alright, if you know the meaning of this, now tell me. E is the derivative of V with respect to R. This is R, dV by dr. And E, the electric field inside the charged shell, is 0. Therefore, what can you say about the electric potential inside the charged shell? Well, the derivative of what kind of a quantity will give you 0? If this E has to be 0, then this V has to be a constant, because only the derivative of a constant becomes 0. Now in the same way, if you use integration, V equal to integral E dr. E is 0. What is integral of 0? If you integrate 0, what do you get? A constant. So what is the electric potential inside a charged shell? Well, the electric potential inside a charged shell is a constant. In other words, everywhere inside the shell, the potential will remain a constant. Consider a spherical shell of radius r carrying a charge q. In order to find the potential at any point outside the shell, if you want to find the electric potential outside the charged shell, you have to assume that all the charges are concentrated at its center. We talked about that in the last class. Now, potential at a distance r from the center of the shell, therefore, is Vr is kq divided by r. And this is valid only for points outside the shell. Well, thus the potential on the surface of the shell, what is the potential on the surface of the shell? Is kq over r, where r is the radius. So, the potential on the surface of the shell, everywhere on the surface of the shell, the potential will be a constant, and that will be kq divided by r, where r is the radius of the shell. And at any point outside the shell, the potential will be kq over small r, where that small r is greater than the radius. So if you go away from the shell, the potential decreases, right? The potential has a maximum value at a point on the surface. As you go away from it, the potential decreases. All right, now tell me, we just found out that the potential at any point on the surface is kq divided by r. And we also said earlier that the potential inside the shell is a constant. Now what will be that constant value? It will be the same as the potential on the surface. So the potential at any point on the surface and at any point inside the shell will be kq over r. The potential at any point inside will be a constant, which is the same as the potential on the surface. So the potential on the surface of a charged sphere is kq divided by its radius. Inside the shell, the electric field is 0, and so the potential must be a constant. Since the potential on the surface is kq divided by r, it means the potential at any point inside the shell also must be equal to kq over r. Alright? So, potential at any point inside the shell and at any point on the shell, the potential is uniform, is given by kq over r, and potential at any point outside will be kq divided by small r, where small r is the distance of the point from the center of the shell. What is the meaning of equipotential surface? The name itself suggests what it is. Equipotential surface. A surface where the potential is the same all over is called an equipotential surface. Now tell me, is the surface of a charged sphere or a shell, is it an equipotential surface? Yes, we just said potential at any point on the surface of a charged shell or a charged sphere will be kq over r. Therefore, the surface of a sphere, a charged sphere, is an equipotential surface. A surface where the potential is the same all over, is an equipotential surface. The electric field on the surface of a conductor, we talked about it. You have a charged conductor on the surface. The electric field always is at right angles. So the electric field on the surface of a conductor is perpendicular to it, since there is no field on the surface. That means the surface of any charged conductor, you see, you take any charged conductor, irrespective of the shape, the surface of the charged conductor is an equipotential surface. Why? Because the electric field on the surface of a charged conductor is zero. I showed it to you in the last class. If the electric field is not perpendicular, if the electric field is like this, then there will be a component along the surface. And if there is a component of electric field along the surface, it will make electric charges move on the surface. And since it does not happen, we know there is no electrical field component along the surface. That means electric field is at right angles to any surface that is charged. Now, if the electric field is at right angles, there is no electric field along the surface. If E equal to 0, that means the potential is a constant. So, the conclusion is the surface of any charged conductor is an equipotential surface. The potential at any point on a charged conductor will be 0. Since E equal to 0 on the surface, V, the potential, must remain a constant. Very important. Now, you can see the surface is an equipotential surface. How about this surface that I have just drawn? Well, you can actually draw many surfaces as long as the electric field remain at right angles to the surface. You know that there is no electric field along that surface. Therefore, that surface also is an equipotential surface. You see that? If you have a surface that is at right angles to an electric field, it is an equipotential surface. All right. Irrespective of the shape of a conductor and the charge it carries, the surface of a charged conductor is an equipotential surface. Equipotential surfaces can also be constructed outside a conductor by drawing a surface that is at right angles to the electric field. Any surface that is at right angles to an electric field is an equipotential surface. The potential at any point on that surface will be the same. Let's now talk about distribution of electric charges on a conductor. Now, let's look at a couple of conductors. If I have a conductor like this, and if I charge this, how would you think the electric charges are distributed? Will there be regions where charges accumulate, and will there be regions where there will be very few charges? Or will the charges be uniformly distributed? Well, that is what we're going to talk about here. Distribution. How are the excess charges distributed? All right. Now consider a conductor of this shape. Well, it is kind of a pear shape. Doesn't matter. Some irregular shape. Now, let's consider two regions of that conductor. This is region A and that is region B. If you look at A is, well, is part of a sphere of a certain radius. Tell me which of the regions, A or B, has bigger radius? A has larger radius. If you construct a sphere around the region A, the radius of that sphere will be greater than the radius of the sphere at B. Is that right? Okay. Now, the radius of curvature of the surface is greater at A than at B. If R1 is the radius of curvature at A and R2 the radius of curvature at B, then you know R1, the radius of curvature at A, is much greater than the radius of curvature at B, that is R2. If sigma 1 is the surface charge density at A and sigma 2 is the surface charge density at B, then approximate expressions for potentials at A and B can be written as, you see, if sigma is the surface charge density and R is the radius, then you can write an approximate relation for the potential at a point on the surface as potential is sigma multiplied by the radius. Well, I'm going to leave it for you to figure out. It can be done, and it is true. Now that means the potential at A is then sigma 1 R1. Potential at B will be sigma 2 R2. Well, tell me, what is the relation between potential at A and potential at B? Didn't we say just about 5 minutes ago that the surface of a charged conductor, irrespective of its shape, is an equipotential surface? That means the potential at A must be equal to the potential at B. Since the surface of the conductor is an equipotential surface, the potential at A must be equal to the potential at B, or sigma 1 R1 must be equal to sigma 2 R2. What does that mean? It means because R2 is much less than R1, for this relation to be good, the sigma 2 has to be greater than sigma 1. That means if the shape of a conductor is like this, the charge density is going to be greater where the radius is smaller. The charge density is less where the radius is bigger. So, charge density is greater where the radius is small. This means that the surface charge density at sharp corners and pointed ends in the conductor is much greater than at other parts of the surface. For example, if I charge this conductor, look at this conductor. This has a sharp pointed end. That means if I charge this, most of the charges will be concentrated here where the radius of curvature is very small. So when an object is charged, there will be a concentration of charges at sharp pointed ends. Now, in the last lesson, I talked about you getting shocked when you touch your car. I'm sure most of you have experienced it. You see, if you are in the habit of getting shocked from your car, the best way to do that is go and grab the door handle with all your fingers. Don't just go and touch with one finger. You know why? When you are charged, the charges will be concentrated at the tip of your fingers. So if you go and touch with one finger, all that charges will try to jump across at that point, creating a very uncomfortable shock. Whereas if you go and grab, you increase the area, that means you reduce the shock. Now, this has got some very interesting applications. Now, let's talk about dielectric breakdown. Did we talk about dielectric breakdown in the last class? What does that mean? Now, when you charge an object to a very high electric field, now I'm going to say if you charge an object to a very high potential, that will result in dielectric breakdown of the air by producing ions in the air. That means air will become conducting, and that is how you get the shock. All right. Air is normally an insulator. A good insulator is called a dielectric. A very high electric field produces ionization in air and other dielectrics and make them conducting. And this process is called dielectric breakdown. And what is responsible for that? A very high electric field. Now this phenomenon is what we call dielectric breakdown. Dielectric breakdown happens in air at an electric field strength. We talked about it in the last class. 3 times 10 to the 6 volt per meter. Now that is the reason why we got lightning. You know, clouds, when clouds move in air, the rubbing of the clouds with the air molecules create large amounts of electric charges. Now, suppose we have a big old negatively charged cloud overhead. You see, when clouds move in the atmosphere, they are continuously rubbing against the air molecules. That means there will be charges created. So clouds will be full of excess charges. So suppose a big old negatively charged cloud passes overhead. Now nearby conducting ground acquires an induced positive charge, establishing an electric field between the cloud and the earth. Now this is the phenomenon. Here is the cloud that carries a large amount of negative charge, and this is the ground. Because of the presence of these large negative charges directly above the ground gets a lot of induced positive charge. Now that means a very high electric field is now established between the cloud and the ground. And the electric field will be like this. And now, if this electric field is above the dielectric breakdown, that is 3 times 10 to the 6 volts per meter, then the air will become a conductor and the electric charges will discharge through air to the ground. And that is what we call lightning and thunder. And that could be a pretty bad shock if you happen to be in the path. If there are high buildings or trees in the path, you know what will happen. Well, that is due to the dielectric breakdown. If the electric field exceeds the E max, that is the maximum electric field before dielectric breakdown, then dielectric breakdown occurs and a sudden burst of discharge occurs between the cloud and the earth, burning anything in its path, houses, humans, or anything. Now this devastating effect of lightning can be prevented by using lightning arresters. Now what is a lightning arrestor? Have you seen one of those? A lightning arrestor is an arrangement of conductors that have pointed ends. Suppose you have a building here, that's a building, very tall building. Now install on top of the building something like this, spiked conductors and connected to the ground. You know what grounding means. Now when clouds pass by near the building, where suppose there is a build of charges there, now what happens is the presence of these charges will induce positive charges on the spiked conductors. So there will be induced charges on the conductors, and because of the pointed ends, all those induced charges will be concentrated at the pointed ends. And the concentration of these positive charges will gradually neutralize all the negative charges in the cloud. So what does the lightning arrest to do? It will gradually neutralize all the buildup of charges, thereby preventing a discharge. So this is a very useful thing to do for very tall buildings, and in many places in the world I have actually seen lightning conductors. I haven't seen them in Florida, although Florida is called the lightning capital of the world. Well, let me see if I can show you a simulation. Now, this is a simulation of how electric charges get accumulated in the cloud, and as the accumulation happens, you can see they discharge to the earth. And if this unfortunate house happened to be in the path, well, God help us, is that right? Now, it can be prevented by using a lightning conductor. If you have a lightning conductor on this building, that lightning conductor will neutralize the buildup of charges in the cloud, thereby preventing a lightning discharge. Now you can see lightning discharge occurs not only between the cloud and the earth, it also happens between clouds. If you notice, it can happen between clouds. One cloud that is positively charged, another that is negatively charged, can create electrical discharge. Well, that is a good illustration of how electric discharge occurs in nature. Let's now solve another problem. Two horizontal metal plates are separated by 10 centimeters, and an electric field between them has a magnitude of 1 times 10 to the 4 Newton per coulomb, directed from the lower plate to the upper plate, as shown in the figure like this. What is the charge density on the upper plate? What is the charge density on the lower plate? What is the potential difference between the plates? What is the potential of the upper plate if the lower plate is grounded? A small particle of mass m and carrying a charge q is in equilibrium in the space between the charges. What is the charge carried by the object? Alright, let's look at these. The electric field between the two plates is E equal to sigma over epsilon naught. Do you remember that one? The electric field between two parallel metal plates that are charged, each will contribute a field of sigma over 2 epsilon naught. The total field will be sigma over epsilon naught. Therefore, sigma equal to E epsilon naught. That will be electric field is given to us, multiplied by sigma. That will be 8.85 times 10 to the negative 8 coulombs per meter squared is the charge density. Well, we need to find the charge density on the upper plate and at the lower plate. Tell me, the electric field is given to be directed from the lower plate to the upper plate. So, what is the charge on the upper plate? Is it positive or negative? An electric field will originate from a positive and end in a negative. So that means the lower plate is positive and the upper plate is negative. The direction of E suggests that the upper plate is negative and the lower plate is positive. That means the charge density on the upper plate has this negative value and the lower plate has the same positive value. The charge density on the upper plate is negative and the charge density on the lower plate is the same negative value. What is the potential difference between the plates? Well, do you know the relation between electric field and potential difference? The relation between E and V is E equal to negative V over delta X. What is delta X here? Delta X is the plate separation. So delta V equal to negative E delta X. and that will be negative. E is given to us. Delta X, the separation of the plates, is given to us. Therefore, the potential difference is negative 1000 volt. Well, what's the next thing we need to find? The lower plate is grounded, means that the potential of the grounded is zero. Anything that is grounded is at zero potential. And therefore, the potential of the upper plate is negative 1000 volt. It is a negative plate. Its potential is negative 1000 volt. Okay, how about the last part? We have an object that carries a charge Q is in equilibrium in the space. What does that mean? If the object carrying a charge has to be in equilibrium, then the weight of the object acting vertically down must be balanced by the electrical force that must be acting up. So obviously it is a positive charge, because only a positive charge experiences a force in the direction of the field. When the particle is in equilibrium, its weight mg is balanced by the electrical force. You remember, when a charge Q placed in an electric field E, the force on it is Q times E. So when a charged object is placed in the electric field, the weight mg downward is balanced by the electric field Q times E. So QE equal to mg. Therefore, Q equal to mg divided by E. And now we have mass is given to us, and G we know is 9.8 meter per second squared, and E is also given to us. So that charge is 9.8 times 10 to the negative 9 coulombs. Well, that means that will be 9.8 nanocoulombs. Is that right? Okay, I think I'm going to stop this lesson here. We have done now a number of illustrations on potential difference, the relation between electric field and potential, and so on. And this is the end of Unit 3. We talked about static electricity, electric charges, electric field, electric potential, which we will be using in our next unit. So it is now time for your next test. Now go through your practice test and make sure that you are ready for the test before you open it. All right? I will see you for Unit 4 a little while later.